hello everyone. Thank you for coming today, and we will present our work, Phasor-based camera space construction for making radiometric accumulation assumptions explicit. So let me start with our motivation. What we see here is the rendering equation. We are familiar with that, and it's inspired by the heat transfer. And this is the equation expressed in the radiometric form. And for the radiometry, it is initially used to measurement the heat. And now we have two keywords, measurement and the heat. For heat, we mean we are dealing with a thermal source rather than with a laser-like source. It means somewhat degree of the incoherency. And for the measurement, it means we have a sensor and we are doing integration on some dimension. For example, on the temporal, spectral, spatial. And usually in computer graphics, we just accept this assumption and move forward. But today, I want to be a little bit slow down, and I want to unfold this accumulation assumption. I want to see what happened behind it. And I also want to ask if we can do something useful for doing this. And let me start with the construction. So the way we achieve making the accumulation assumption explicit is we proposed a Phasor-based camera space construction. We choose the camera space because we want the overall process to be straightforward and controllable. So we start from taking path tracing, pinhole path tracing input and the depth map. We back project it to the camera space. And the irradiance give us the amplitude of the field. We still need the missing phase. But this is the underdetermined problem. So in this case, we choose a straightforward way. We randomly assign the phase to the field. And it means using a random feature time model. And after that, we decide to slice the scene into multiple layers, and we will propagate layer by layer through the aperture and the scene length to the sensor. Then on the sensor, we will simulate the temporal accumulation by averaging between different realizations, where each realization consists of different phase initialization. And for the wavelength accumulation, we will average realizations with different wavelengths. And unfortunately, in current version, we doesn't support this construction does not support the spatial accumulation. And given this construction, the first question we want to ask is that, is the accumulated result still match the radiometric path tracing reference? And the answer is yes. Let's start with a very simple example. For example, the Cornell box. It's a good example because it only contains the Lambertian emission and the Lambertian reflection. And as we can see here, visually speaking, they look very similar. And for the quantitative result also support that, but they are not pixel-wise identical. We can see that on the light source, in our result, we see somewhat kind of the blurring effect, but for the seamless path tracing, it's not that significant. And also, there are some kind of the blurring effect if you take a close look, and this is one of our limitations. I will go back to this later. And in this slide, we show more case because in last slide, we only have the diffuse surface. In this slide, I show the HIMS, which contains specular reflection. We have space shape, which have transparency, and we have living room, which have a larger FOV. And the conclusion, they are similar. The accumulated result of our construction is still matched with the path tracing reference. And now we have established the consistency. We can be more precise about where the work sits. So for this kind of work, it's very important to talk about the boundary stuff. So our work have intersection with 4 established fields. And we will be clear about what we did and what we not do. And in radiometry, we are not processing new light transport formulation. We use radiometric quantity as a stable endpoint, and we afford the accumulation process behind them. And for the statistical optics, we use the random Phasor model as a controlled statistics model to stay aligned with the radiometric reference. That means we are not actually modeled a physically meaning rigorous incoherent light source. And for wave propagation, we borrowed this layered-wise Fourier propagation from holography, but we are not trying to drive a holography display. We are rendering something, so the content is shift. And for the wave optics rendering, so at least in this work, in current stage, we haven't proposed any novel visual effect that nobody do before. But instead, we are trying to make a hidden process explicit. And with this boundary in place, we can now ask, okay, what does this construction actually give us? And my answer is a little bit long. It's a backward compatible interface for analyzing and rendering phase-sensitive camera space effects. So first, we preserve the endpoint. I just show that our accumulated result it still matches the path tracing reference. It's not the end of the research, but it is the start of the research. Our result only have a meaning based on that. And the second, we expose the intermediates. So if we take a look at the single realization, and it will reveal phase-sensitive interference structure. I will show this later. And the third, this gives us an explicit suppression process. We can directly observe how temporal and spectral accumulation suppress this realization-dependent structure and return to a stable radiometric image. And finally, this also suggests some practical utility. We are not trying to replace the geometric optics-based rendering pipeline, but we are building a compatible camera space interface that can support phase-sensitive post-processing effects. So we have, say, the first one, and I will show the next three one by one. So here we look at a single statistical realization, and at the first glance, it's noisy, and we think we've encountered this many times. But if we zoom in, we will notice that this is not the Monte Carlo noise we encountered usually before, and this is actually interference structure generated by our construction. And we also checked the statistics of this noise in some selected region. The intensity follows a negative exponential like profile, and the contrast is closer to 1. So this pattern shares statistical property with optical speckles. But at here, I need to be careful about the wording. So even though they share the statistical property, but they are not the same thing, because in our model, we are not really modeled a physical, rigorous, incoherent light source. So it's had better to call this pattern something like realization-dependent interference structure patterns. And if you want to figure out the meaning behind it, please take a look at our paper. And due to the presentation time constraint, now I will start to introduce how our process can suppress these patterns. So on the top row, we average the realizations at the same wavelength with different realizations. With different initial light phase. And this is the temporal accumulation simulation in our setup. And we can see from left to right, the patterns, they are suppressed. And in the middle row is the spectrum. Basically, we not only alter the initial phase, we are also averaging along different sampled wavelengths. And as the reference, in the bottom row, we list the regular Monte Carlo path tracing convergence as the reference. So along these three cases, we can see that the visual appearance is different, even though all of these three cases, they are converged to match the configuration. But however, for the first two rows, it is the washout of the phase-sensitive interference structure. And on the third line, it is the Monte Carlo noise reduction. They have similar trend, but they are representing different processes. And this is what we want to make it explicit. So even though the accumulation suppresses those patterns, the propagation, it indeed still happened. And that's where the practical utility becomes interesting. So let me start with a simple example. By just changing the aperture from a circular to the hexagon, I got this diffraction specs, which was described by Huling and his colleague in 15 years ago. And it means that even though the realization-dependent interference is suppressed by accumulation, the camera space wave propagation it still took place, and it means the spatial interference structure still left some visible trace. And this is why we describe our construction as a potential post-processing plug-in. And it let us introduce some camera space effect without replacing the whole geometric rendering pipeline. And there is also a methodological idea I think it's very interesting. So our phase completion is underdetermined. And this is very similar to the spectral reconstruction. And in both cases, we start from the visible quantity and we try to complete some higher dimensional representation. We do some useful operations in the high dimensional space, and then we class back to the observable result. And for looking ahead, one natural step is we want to support not only incoherence like initialization, we also want to support partial coherent initialization. And before the closing, we should separate between the limitation and the theoretical boundary chosen by us. So on this slide, I list the limitation and the boundary. So for the limitation, the main limitation of our work is that, remember that we get the texture from the path tracing. So we are propagated using textures. And each pixel in the texture, it represents a physical area in the camera space. And since we assign only a single phase to it, it means the field in this physical area, it is perfectly coherent, and this is not what we want. And secondly, we don't have spatial accumulation within the pixel. And these two together may help to explain why we have blurring artifacts shown before. And for the boundaries, for theoretical boundary, we intentionally choose to operate strictly within the geometric optics-based rendering assumption. It means we are not trying to model in like the polarization, the light-matter intersection, or full scene wave propagation. And as the result, the pattern I shown before, the intermediate pattern I shown before, it only has its explanatory value exclusively in this setup. And all in all, if we go back to the beginning, we are trying to unfold, we are trying to instantiate the assumptions. We are not trying to breaking it or surpass that. So for the first limitation, we are actively seeking to resolve this problem. But for our technical boundaries, we will be very careful about extending the boundary, because the more boundary we break, the less backward capability we have. And for the conclusion, we are trying to unfolding radiometric accumulation assumption within the camera space. We proposed a construction. We computing camera space irradiance into phasors and propagated them to the sensor and accumulate on the sensor. We show the endpoint consistency. So the final image is closely matched with the seamless path tracing reference under the matched camera configuration. And at the same time, single realization reveals interference structure that is usually hidden by those assumptions. And the temporal or spectral accumulation progressively suppresses that structure. So this work gave us a controlled way to explain a normal hidden stage in the image formation, while staying backward compatibility with the existing rendering pipeline, and suggests a practical post-processing usage. And thank you very much for your time. I'm happy to answer the questions.
Okay, thank you. We have time for like one or two questions around there on the back.
Okay. So thank you for the great talk. So you said that interference statistics follows negative exponential distribution, which is related to fully developed speckle.
Yes.
And I wonder how you evaluated the distribution. What I mean is, so did you use enough sample per pixel to get the converged result? I wonder what would happen if you do not use like sufficient number of sample, like 1 SPP, then how would that distribution look like? And I wonder, for in general, how many samples do we need to get that kind of converged distribution?
So thank you for the question. So for this image, I take from a single realization, and with around the light source area around of the cornea box. So this is from single realization. If I have many samples, then if I have many samples averaging together, then it will converge to a stable image. Then we don't have the contrast and we don't have this distribution. So I think the answer is 1.
So what I asked is, like, if you use low SPP, then like noise from Monte Carlo process and noise from the speckle would be mixed. And I wonder if you could like.
Sorry, can you maybe explain the question in another way?
So what I mean is like, so how many SPP do you use to get this forward?
1 single realization.
Single realization.
Yes. So this is we don't. I think it for this one we don't have the concept of the SPP. It's like we have initialize the phase construction, and after propagate, it's just 1 realization. It's not a Monte Carlo convergence. I don't know if I don't know if my explanation is clear.
Okay, but yeah, I'll ask later.
Okay, sorry. I think I will answer the question after the QA session.
Do you have any more questions? If not, I will just make one. So I understand that you first path trace through pinhole camera, and then you just randomize the phase and then propagate back to an aperture plane, and that's what you get for. Have you considered, because then you have to do a lot of layers and then you propagate each one of them. Have you considered directly like propagating from this last vertex in the surface to the aperture directly as if it was an irradiance sensor? Like, so every pixel in the aperture plane, which is like the intermediate plane, is composed of, I mean, it's measuring everything you see on the scene, like in a hemisphere, let's say, and randomizing the phase at that regard, I mean, in that point. I don't know if, so instead of pinhole, I mean, having a pinhole camera model, where you render like a clean render, and then you randomize the face as a texture, and you propagate back to the plane. You could directly, during the Monte Carlo path tracing, you could, in the last segment between then you can just randomize the face at that point. Have you considered that, or it would be interesting to do that for some reason, or?
I not quite understand the question. So You mentioned about the pinhole and the thin lens, right?
Yeah, so instead of rendering a pinhole camera,
Yeah.
you directly trace from the aperture plane, which is your final, where your final image, I mean, the final signal are going to be collected. You could directly trace from every point on to the scene.
I see.
Take into account the distance as your RSD, your Rayleigh Sommerfeld.
I see. I think that's a good point. I choose this approach because it's the most straightforward approach. I think for the future extension, I think it is a very good direction.
Okay.
Does that answer the question?
Yeah. Thanks. We got it. So, any more questions? Okay, then let's thank the speaker again. And